Okay, so hi everyone. This lecture is about radiation field quantities important in our study of ionizing radiation dosimetry. I will be using the International Commission on Radiation Units and Measurements report number 85 titled Fundamental Quantities and Units for Ionizing Radiation, the revised version, as my main reference. Let's start. In our discussion of fundamental quantities and units for ionizing radiation, we will use the ICRU, or International Commission on Radiation Units and Measurement, report number 85 as a reference. ICRU, since its inception in 1985, is the main responsible in creating or developing internationally acceptable recommendations regarding the following. So first, quantities and units of radiation and radioactivity. Second, procedures suitable for the measurement and application of these quantities in clinical radiology and radiobiology. Last, physical data needed in the application of these procedures, that includes the use of which tends to assure uniformity in reporting. The Commission also considers and makes recommendation for the radiation protection field. With this regard, it has a close cooperation with the ICRP, or the International Commission on Radiological Protection. In discussing radiation field quantities, it falls naturally into pairs, referring either to first the number of particles or to the energy transported by these particles. Radiation fields consisting of various types of particles such as photons, electrons, neutrons, or protons are characterized by radiometric quantities that apply in free space in matter. Shown here is the ICRU, or the ICRU sphere, that we will use later to describe certain radiation field quantities. In characterizing the radiation field at a certain point P, we will use this illustration here in terms of the radiation traversing a sphere of cross-sectional area dA for the infinitesimal cross-section centered at a certain point P. So this is a sphere S, with a volume V, or dV, with a mass dm, and this is our radiation rays. In discussing radiometric quantities, we start with the definition of the number of general quantities associated with the radiation fields, namely the particle number n and the radiant energy R. The specification of the radiation field can be discussed by differentiating both n and R with respect to time, area, volume, direction, or energy. We will describe N and E, these two quantities here, in terms of their distribution. The distributions NE and RE of the particle number and the radiant energy with respect to energy are given by the following. So we have this one, N sub E and R sub E, where Dn and Dr is this one, the number of particles with energy between E and E plus dE, the infinitesimal dE, and dr is their radiant energy. The two distributions are related using this first assumption. For monoenergetic E, the radiant energy R is described as the product of your N times E. For your radiant energy, therefore, we can arrive with this relationship. We can also describe the particle number n and the radiant energy R with respect to their volume as shown here. So we have the particle number density n and the radiant energy density U, where dn here is the number of particles in the volume dV and dr is their radiant energy. This distribution N sub E, we also have U sub E, as shown here, of the particle number, density, and the reagent energy density with respect to energy are given as follows. Thus, we can have the relationship of the two distribution as shown. Next, we have the flux and energy flux. The flux is the quotient dN by dt, where dN is the increment of the particle number in the time interval dt, while the energy flux with the unit of watts is the quotient of dr by dt, wherein r here, or dr, is the increment of radiant energy in the time interval dt. These quantities frequently referred to as a limited spatial region, and one example is the flux of particles, let's say, emerging from a collimator or from a certain source in all directions. The fluence with the symbol of this capital Phi is the quotient of dN by dA, wherein dN here is the number of particles incident on a sphere of cross-sectional area dA, as shown. The energy fluence, psi, is just the quotient of dr by dA, wherein dr here is the radiant energy incident still on our sphere of cross-sectional area A, or dA. The use of a sphere of cross-sectional area dA expresses in the simplest manner the fact that one considers an area dA perpendicular to the direction of each rays or each particles. The quantities fluence and energy fluence are applicable in the common situation in which radiation interaction are independent of the direction of the incoming rays or particles. We can also describe fluence and energy fluence in terms of their distribution or energy distribution. So we have the following. We have your capital phi E sub E, and we have your psi sub E, wherein our d phi here is the fluence of particles of energy between E and E plus dE, while your d psi here is their energy fluence. The relationship of the two distribution is given by this. So your psi sub E is equal to E, the energy, times phi sub E. In dosimetric calculations, fluence is frequently expressed in terms of the lengths of the particle trajectories. So we have your fluence phi here, which is equal to dl over dv, wherein dl is the sum of the lengths of the particle trajectories in a certain volume dv, while if the radiation field does not vary over a time interval t, we can define your fluence phi as follows: nvt, wherein n here refers to the particle number density, v is the velocity, and t is the given time interval. We can also express fluence and energy fluence in terms of their time derivative. So we have their fluence rate and energy fluence rate as shown. In radiation transport, it is also called a particle flux density for the fluence, while for the energy fluence, this is also called energy flux density. Your d's psi or d phi here refers to the increment of the fluence in the time interval dt, while for the energy fluence density, the d psi here is the increment of the energy fluence in the time interval dt. Also, if for a radiation field composed of particle velocity v, the fluence rate can be expressed as shown, wherein n here is the particle number density and v is the velocity. Now let's define first solid angle. Suppose we have this cone of direction from a certain point. This certain point can be the center of the sphere. what we want to do is to project this set of direction into a unit sphere. This is our unit sphere, this color green here, and the measure of the solid angle is called steradians. This is your solid angle with the symbol of capital Rho. The solid angle is also described as the area that intercepts on a certain unit sphere, or we can also describe this one as the measure of the amount of the field of view from a particular point, or the measure of how large the object appears to an observer. Just like a planar angle in radians, which is the ratio of the length of a circular arc to its radius, a solid angle in steradians is as follows. So your capital Rho is equal to A over R squared, or the Rho is equal to dA over R squared. So thus, for this given configuration here, for a sphere, we have your polar angle theta and your azimuthal angle phi with this radius r. We can have the following expression for our d rho, or for our solid angle, and this is equal to sine theta d phi. Now we'll define particle regions and energy regions in terms of fluence rate and energy fluence rate. Particle regions is expressed as the fluence rate over the solid angle rho, or d rho, while energy regions is described as the energy fluence rate of particles propagating within a solid angle uh, d rho, shown. For the spherical coordinates with the polar angle of theta and azimuthal angle of phi, small phi, the solid angle d rho is described as sine theta, d theta, and d phi. The distribution of particle regions and energy regions with respect to energy are given as follows. So first we have for the particle regions, then we have for the energy regions. The two distributions shown here are related by this equation. So the distribution for the energy regions is equal to E, the energy, times the energy distribution for the particle regions. This quantity here shown is sometimes termed as angular flux or phase flux in radiation transport theory. So these quantities are the last quantities that we will discuss for the scalar radiometry part. Hey guys, I hope you have learned something in this video. If you like my content, please consider subscribing my YouTube channel, JP Academia. And if you're new in YouTube, there is a button right down below this video. Just click that to subscribe. See you then. Bye guys.